Here we go again. This is how a lot of you already know. This is a webinar series. So we are here to the second appointment with our webinar series. Like I said, this is the second one, and we will go on practice in this one. A lot of you already know where in the first one, were participating in the first one. And for those who didn't participate, the first one is really interesting too. You should go and check it on our website or on our channels, LinkedIn and YouTube. You will find the registration. And it was a general presentation of the board, and we had a guest from u-blox participating in it. So go and check it after this webinar. So I would like to say thank you to everyone that were in the first one, and it's again here. Yeah, if you have any question during the presentation, that it will be a bit technical, so it's okay to have questions. Just type it during the presentation in the chat. So we will leave a bit of time in the end to reply them. So let's start. You should see my screen here. Okay, should be online. Can you confirm it, please? Si vede. Perfect. So here we are. Our Cicerone board, like a lot of you already know, we spent the last weeks speaking about it with some of you. It's a form factor Arduino board, and integrates our MAM-WL and GNSS from u-blox. So today, like I said, we will do a bit of practice, a practical example, and to introduce who will be speaking, I'm Ilenia Carola. I'm the business developer of MoveX. So I'm in charge of everything can foster the growth of MoveX in general. Then we will be having speaking our two electronic design engineering, Igor Tardiota and Alessio Moro. Igor will be running an introduction to the firmware development and the programming of the Cicerone board and in general of all the MAM-based board. And Alessio Moro will be running a practical example of an asset tracking application of the Cicerone. So, like I said, we already had a meeting, a webinar about the introduction, general introduction of what Cicerone is, and of the two main characters of this board that are our radio module LoRaWAN and a GNSS from u-blox. I will remember you that you can find it on our channels and on our web. So just for those who were enjoying the first one, a quick introduction. This is our board. This is the Cicerone board. It's a form factor Arduino board. And the first character in the board, it's our MAM. It's our first product, and it has a lot of success already. It has been integrated in a lot of applications, and it's a low power LoRaWAN module. It's designed to be a small size with a powerful SD core. And something that is really important for us when we designed it, we wanted something that reduces the BOM, optimizing the supply chain and the certification. In fact, our module is fully certified. And then the second character of the board is the Max M10. It's the best in class of u-blox GNSS that integrates this full service from u-blox, that is the CloudLocate, that can make you allow you to save even more energy. So in the first webinar we spoke a lot about it, and it's really a cool service from u-blox. So in the past week, I had the pleasure to speak with a lot of you about the applications that you wanted to develop with the board. And so I heard about drones, tracking application in general, really cool stuff. And we decided the board for tons of application, such as smart agriculture. We are speaking about cattle monitoring, field monitoring, a lot in the smart cities. So everything that are related with lighting, smart parking, means also in the smart industries, asset tracking, smart logistic, thief detection. But those are just some of the application of the Cicerone board. And every week I'm hearing from you a lot more application, cool stuff. So I will leave the work to our engineers so they can run the practical examples. The first one is Igor. Igor, can you join us?
Hi, Ile.
Hello.
Hello, everybody.
Hello. Thank you, Igor. I will leave you the sheet.
Thank you too. Okay, so just a minute. I will share the presentation. Okay. Are you able to see? Okay. So, hi everyone. I'm Igor Tardiota, electronic engineer at Movex company. And today, with the help of Alessio Moro, we will show you some interesting aspects about our main product, the MAM WLE module and the newest Cicerone board. This will be a technical quick guide for programming and use the MAM WLE module. It is addressed to companies as well as private users. So let's start. When you want to create a new application involving our MAM WLE module, that is also the heart of Cicerone boards or your sensors, you will need a software running inside it. In fact, the module, being capable of both LoRaWAN communication and standard microcontroller processing to interact with sensors and actuators, needs its firmware. So how it is possible to program the MAM WLE? Well, if you read at the technical documentation available on Movex website, you will find out that the MAM WLE contains an STM32WLE microcontroller from ST Microelectronics. The company provides the STM32Cube free software suite containing the CubeMX, the CubeIDE, and the Cube programmer utilities. The first one, the CubeMX, is a code generation tool for fast development of base firmware. The CubeIDE is instead an advanced environment for writing and debugging C code. that will be running on microcontroller. In addition to this, we have some useful ready-made examples configured for MAN-WLE. You can find them on MOVEX GitHub page as shown in figure. They are a good starting point for new firmwares. Please read carefully the README inside each repository. Now I will show you a quick step-by-step process for firmware creation using STM32CubeSuite. Let's consider a typical scenario. Your sensor needs to communicate through LoRaWAN to send the sensor data. The resulting embedded device is considered as the so-called end node device. We will start with the CubeMX utility. After downloading the end node example, we will open it, obtaining something as visible in the right picture. Here, you can, for example, configure the keys used for LoRaWAN network server, the region of interest, and much more. Imagine that your sensor has an I2C interface. So you'll click on Connectivity tab and set up the connection properties. When you're done, you can click on the Generate button. After that, you can open the STM32CubeIDE program. Here, you can add some other user code relative to the desired application you want to create. The end node example implements a simple data transmission. It sends the LoRaWAN server an incrementing counter on a certain port every 10 seconds. Imagine that this is what you would have done by adding user code. Let's see how this is implemented. In the main code, there are some basic hardware initialization. Before entering the main loop, not shown in the picture, there is the last initialization called with the MX LoRaWAN init function. Inside it, there are the system and the LoRaWAN initializations. We'll focus on the last one. The end node example is based on the sequencer software utility. It is a sort of simplified operating system. Each task is first registered and then set every time you want to schedule its execution. The scheduling is typically handled by a generic timer, configured to call one time or periodically the set function. So we first create the timer handle, then we'll start it. When I reach the desired period value, 10 seconds in this example, it calls in interrupt mode the onTX timer event. Inside the function, the user task used to send the counter value is scheduled by setTask function. Finally, when the sequencer executed, it will call the sendTXData function as previously declared here. sendTXData, the message consisting of a single byte is prepared and sent through LoRaWAN. One of the advantages of using such an approach is that when there are no tasks to be executed, the microcontroller can go in deep sleep mode, reducing the power consumption down to a few tenths of a microampere. Now that the code is ready, you can debug and/or program it. Let's say we want to program the Cicerone board. You will typically use an ST-Link programmer connected to the ST-Link port, as in figure. You need to connect also a power source, for example, connecting the micro USB cable to the computer. Click on the Debug or Run button from the IDE menu, and you are ready to use your program device. All the things I explained so far were intended for generic MAN-WLE-based devices. With the creation of the new Cicerone board, we released also an Arduino IDE support package. The Cicerone board, in fact, is an Arduino-like board with MKR form factor. In this way, the support package lets you writing and programming a firmware directly into the Arduino IDE, as you normally do with other Arduino boards. It enables a fast prototyping, writing a full end-on example in a few minutes. To start using the Arduino support, you can go to our MOVEX GitHub page and take a look at the MOVEX Arduino repository. There, you will find all the useful instructions to start with. It is constantly updated. Every time a new feature or a bug fix is made, and your Arduino IDE will notify you the presence of the update. It is really cool. The support package includes different examples for LoRaWAN communication, for using a u-blox GNSS module, and for using the peripherals present on the Cicerone board. To program the board, you can simply use the standard upload button after connecting the board via USB. Okay, so hope that this quick guide helped you to understand what is the approach to the firmware development of our MAM-WLE-based devices. And now I'll give back the floor to Elenia. Thank you.
Thank you so much, Igor. Thank you. Really cool stuff. So that's the turn of Alessio. Hello, Alessio.
Hello, good evening, everyone.
Hello.
Hello.
So I will leave you the word to speak and to a practical example.
Okay. Hello, good evening. Thank you for joining us. My name is Alessio Moro. I'm a design and application engineer at MoveX. And today we will cover an asset tracking application using the Cicerone board from MoveX. Let's start sharing the screen. Can you see it? Okay. Okay, so asset tracking applications are, sorry, I lost the pointer. Okay. Asset tracking application are a set of applications that applies to different industries, such as monitoring of position for containers, for machinery in farms and construction sites, and so on. It also applies to smart cities as a huge spectrum of possible target industries. All of this kind of application, however, share the same requirements, which usually are long battery life, because we want the device to be to has a low maintenance, so low cost of running the monitoring service. Small size in order to be embedded into bigger machinery, such as, for example, in smart cities, we want devices to be small and unobtrusive, for example, for monuments or appliances. And other typical properties of the asset tracking is that you don't need the device to know its own position, but what you need is to have its coordinates available on the application server. For example, to be shown on a cloud platform to the user, and where they can be processed and analyzed by the end user. Finally, one last item is that the application area usually is known previously of the installation. This means that we can be sure that the coverage for the connectivity is available. And in case it is not, using LoRaWAN, what we can do, we can install our own gateway, since it's not provided by official providers, but LoRaWAN is based on ISM bands, which are free. So the users can install its own gateways and its own private network if needed. Okay, typical architecture of this kind of solution go down from the end node up to the application server in this block diagram. we have the Cicerone board as the end node, which provides LoRaWAN connectivity thanks to the MAM-WLE module on board, and it also embeds GNSS positioning capabilities thanks to the MAX M10S module by MoveX, which both modules are optimized for low power, and this low power consumption is matched by possibility to power the board through the battery, and the board also has a battery management circuit that provides that makes possible to recharge batteries connected through the connector. Compatible batteries are LiPo 1 cell, 3.7 volts usually, and with the size of batteries can be dimensioned based on the application. Here we can see also the typical LoRaWAN architecture, where we have the network server as the center point of the network. Then we have gateways, which are simple devices that collects LoRa packets from the end nodes and forwards them through internet connection to the network server. Network server does the data duplication and the network management, and forwards the acquired data to the application server, which is in charge of the user, and it's customized for each application usually. In this case, since we are interested in positioning, the application server talks also to the CloudLocate service from u-blox, which is a service that we'll cover later, that allows to decode messages coming from the Cicerone board that are optimized in order to have a small footprint in terms of number of bytes for the package. Because as we know, LoRaWAN has a low data rate, because it has low power and it has long range. So the trade-off is, of course, to reduce data rate. And so by enabling uses of small packets that embeds the GNSS position, we can forward the position through the LoRaWAN and decode them later using the u-blox CloudLocate service. Once the coordinates of devices are available on the application server, this can be shown to the user, for example, through the cloud platform or application on the desktop PCs or so on. Why the Cicerone board? Because it embeds the MAM-WLE, which is a very flexible LoRaWAN compatible module. It embeds an STM32CubeIDE family microcontroller with SX1261/2 LoRa radio. This model is optimized for being low power, for having a quality onboard radio front end. It has a high power Cortex M4 microcontroller, which is very powerful and can allows the user to implement also complex processing of data, complex algorithms, and so to have processing on the edge of the network. By having access to the main microcontroller, this means that the same microcontroller can handle both the LoRaWAN stack and the application code from the user, as Igor showed previously. So basically what you have is that you don't need another microcontroller on the board. So you have the MAM-WLE that, thanks to its huge connectivity, flexibility, and large amount of onboard peripherals, can interface many external sensors and the expansion board for the Cicerone board. In this application, the MAX M10S is used through the MES50 command, which makes possible to have a 50 byte length data messages which contain data from the satellites. This kind of usage for the GNSS module allows to have a small message that can be forwarded through LoRaWAN to the application server in order to be decoded by the CloudLocate service, as we in this slide. This is a perfect match for LoRaWAN, thanks to this fixed length of the message and to the low power consumption, which is reduced by the fact that processing is done on the CloudLocate servers from u-blox. So the embedded microcontroller in the u-blox module doesn't have to do all the complex process that is typical of the traditional GNSS positioning. Okay, we'll now cover an example application. In this case, we chose to simulate a renting office that provides users bots for rent. For example, what we will need on an end device for this application is having the position of the boats on the lake, and also having, for example, information about the boat status. In this case, we would like to know if the boat is capsized, so it's flipped upward. So in this case, we can trigger a rescue service for the users. This is our prototype that we built for this application. We can see the Cicerone board powered by a LiPo battery. We can see the MAM-WLE connected to the LoRaWAN antenna. This one is an 868 megahertz antenna. Then we have a GNSS passive antenna connected to the GNSS RF connector of the board, which is an antenna for the L1 band GNSS. And finally, on the right, an accelerometer that is used to detect the board capsizing. Okay, so what the device does? It connects to the LoRaWAN network using in this case, we chose the LoRaIoT provider of network server, which also has a free account that can use it for testing purposes to register up to a few devices for testing purposes. We will use the CloudLocate service for decoding data packets, and we'll simulate an application server using a Python script that acts as a backend for the platform, and also as a front end as a desktop application with a GUI. The firmware interface towards the application server is through LoRaWAN, of course, is implemented using the Arduino package. So the board is programmed using the Arduino IDE. This is because we wanted to have an easier approach to this application in order for the users to understand how the code should be structured and how typically a device works, or a device of this kind works. We use the liblRawan library and the u-blox GNSS library. The implemented kind of packets are an uplink and downlink. We have position uplink on one port that is which all the MAS50 message from the u-blox module are sent to the server. This kind of packages are sent every 60 seconds, which is a typical delay for this kind between packets for this kind of application. But of course, what we have is that higher frequency in sending packets means higher power consumption. So in case we wanted to move the trade-off more on the battery power, battery duration, what we can do, we can rise this delay. We have then capsizing alarm packets on another port, and then we have possibility to send downlink in order to schedule turn on and turn off of the LED on board, which is used to notify the user, for example, for when the renting time is elapsed. The implemented state machine of the firmware handles many different states. First of all, it checks that the network is joined, and once this is done, what it does, it constantly monitors the accelerometer data, and when it detects that the board is capsized, it schedules send of an alarm message to the network server in order to notify the rescue service. Then, otherwise, if the board is in normal state, it gets the position from the GNSS service and forwards it through LoRaWAN to the application server. These are the functions registered in the lib LoRaWAN. We have the user loop where the main user code runs, and this is, in our case, is executed every 1 second, and so the state machine is clocked with a 1 second period. Then we have callbacks functions for join event, downlink packet event, and then since this uses the microcontroller low power mode, it also has a function that is called when the low power mode is entered and one when this power mode is exit. So user can reinitialize devices, for example, that will be used. In this case, for example, I2C, which is used for talking to the GNSS module and the accelerometer. This firmware example is very simple. So the keys are hardwired into the code itself. In this case, we chose to use the OTA activation with keys provided by LoRaWAN server, and this UI, join UI, and keys can be copied into the code, compiled and uploaded to the device in order to implement the end node prototype. Application server can retrieve data with, in our case, with a Python script that uses WebSocket connection to get the uplink data and schedules downlinks through the post request in order to send downlinks to the device. And this is the implemented front end. So this is a basic GUI for made in Python. We have a debug print of the transaction coming from the network server. We have two instantiated bots, and for each one we have a position, distance from the base of the renting server, and information from the last seen event. Then we have a button for scheduling a return request, so to notify users to come back to the base, which is done by scheduling a downlink to the end device, which at the end turn on the LED on the board. And on the bottom, last item is the capsize alarm, which is triggered by the messages coming from the board. Once the board detects the positive acceleration on z-axis, which means that the board is upside down. Okay, so this application server, what it does, going back a little bit, it collects we have the u-blox module collecting position fix from the GNSS. it embeds the data into a 50-byte length message, sends it through LoRaWAN to the application server. The application server talks to the CloudLocate service to decode this 50-byte length message into actual coordinates, and then show the coordinates into a data visualization system. For example, Cloud Platform, in our case, it is a desktop application. Okay, so here is our example. I hope you enjoyed it. And I give back the word to our host, Ilenia.
Thank you so much. Can you see me again? Yeah.
Yeah.
Okay. So thank you so much for the example, Alessio. And I will say that nobody will try to steal a vote again on a lake, thanks to Cicerone and your application. Let's see. So I would like to sum up a bit and to give you some useful information. So information that we didn't set till. Can you see my screen right now? Yes. Okay. Perfect. So some information that we missed. It's that our Cicerone board is perfectly programmable with the Arduino IDE. Also on our web, you will find the application notes. Some examples are written by our engineers that are really useful to program the Cicerone board. And also on our web, you will find the link to GitHub. It's really complete with all the information, so you should check it if you want to prototype something with the Cicerone board, and also the datasheet with all the technical information. So you will find everything on our website. I already saw that you sent some questions. So I would like to leave some space to answer them. Let's start. I will start with this one. So do you know who wants to reply to them? Okay, we'll just say one, and one of you can reply. So first one, does the module make possible to implement low battery alert mechanism? Igor or Alessio want to reply?
Yes, I can reply to Maurizio Manetti. Thanks for the questions. So you asked, I understand the battery can be synchronous needs. Is that correct? Yes, you can use every battery you want. Take care that the recharge current is 200 milliamps. In a typical asset management scenario where not a continuous polling of sensors is required, what is the typical current consumption? Yes, when the Cicerone board is in deep sleep, it consumes only 17 microamps. So it is very low power consumption. Does the module make possible to implement low battery mechanism? The voltage battery is connected to a channel of the internal ADC. So you can monitor the battery level every time you want.
Okay. So if that's all, we have another question from Anibal Bustigio. So first one, are you using Cayenne or similar process to introduce the payload of the data sent to the LoRaWAN gateway? And also, Anibal again, can you explain in more detail how are you using u-blox location services? Does the tracking capabilities rely 100% to the use of such a device as a service?
Okay, thank you for the question. The u-blox location services are available as a cloud service through APIs, so typical post-REST APIs, which are easy to implement in an application server. Yes, in this case, in this application, we implemented the GNSS positioning using only this kind of service, but the Max M10S also allows to use a traditional GNSS positioning that doesn't need any external service to run, which is typical, for example, for satellite navigation. The advantage of using the CloudLocate is that you have very small messages. In the application, we use the MES50 kind of command, which returns from the modules a message that is 50 bytes length. But it's also possible to use other commands that has even a smaller message. For example, there is the MES20 and then the MES12 messages, which has 20 bytes length and 12 bytes length. So no, in this case, we don't use Cayenne to reduce file size because the messages are already prepared by the u-blox module. Okay, but as I said, there is possibility to use the traditional GNSS positioning. So the model will, in that case, will use more power, of course, because you need to power up the module for longer periods of time, and because all the processing is done on the module itself, so the algorithm will take some computing power, so some power consumption, more than the case with the CloudLocate service. But of course, it's a choice of the application developer to use one or the other, or both mixed in the same application for covering both sides of the problem.
Okay, so thank you so much, Alessio. We have just one question left. Gianole asked if he can have, everybody can have an application example of code.
Sorry?
We have Gianole asking, can we get the application example code? The code of the example.
Yes, of course. The code will be available after the webinar on the MoveX website. So have a look at it in
yeah. Also, Also, this registration, you will find it on our web. We will share it on LinkedIn. And also we will send you an email, so you cannot miss it. So don't worry, you will find it. So I will say that we don't have any question left. So if you have more question after the webinar, you can just type us an email here in our at our email address, and we will be happy to reply to you. So I will say that that's all. Thank you so much for participating. We will have more webinars, and we will share the date and all the information soon. So thank you so much, and see you next date. Thank you, Alessio, and thank you, Igor.
Bye.
Bye.
Thank you.
Bye.